Hello, welcome to today's topic. Today's objective will be to identify trends in period 3. We will be looking at trends such as atomic radius, ionic radius, electronegativity, metallic characteristics, oxides formation, and melting points. Let's begin. Before we look at trends in period 3 elements, it is very important to remember that atomic number increases as you go across the period. Now, that will affect atomic radius, ionic radius, and the other trends that we will look at. Now, going across the period, we will decrease in size. What is the reason for that? There is an increase in the attractive force acting on the same shell. Now, the attractive force will increase as you go across the period because you are increasing in one more electron and one more proton as you go across the period. Now, one more electron and one more proton will increase the attractive force. Now, let us say that we are in, say, period 2. Period 2 elements consist of lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon. How does the atomic size or radius changes as you go across the period from left to right? You'll notice that we have 3 electrons present in lithium, 4 present in beryllium, 5 in boron. We are increasing in one more proton and one more electron. So the force of the nucleus is becoming greater. Do you remember what we discussed in the last lesson? If you belong to the same period, you have the same number of shells. So the shell is not changing. The number of shell is not changing. What is changing is the amount of electrons that is being added to the same shell as you go across a period. So if that is happening, it simply means that the attractive force between the outer shell and the nucleus must be increasing, which will pull the electrons closer, hence pulling the shell closer, giving the atoms a smaller radius as you go across. So, lithium should look something like this in terms of its size. Beryllium will look, let's put Li there, and I'll just draw the outer shell. Let's do beryllium, which is 4. So lithium is 3, beryllium 4 should be smaller because now I have 2 electrons being added. And of course, boron should be even smaller because now I have 5 electrons, 2 on the inner shell and 3 on the outer shell. So here I have lithium, and lithium would have 2 on the inner shell, 1 on the outer shell. Beryllium would have 2 on the inner shell and 2 on the valence shell. Boron would have 2 on the inner shell and 3 on the outer shell to make it 5, and so on. So as you go across, the size of the atoms, they are becoming smaller because as you add one more electron and one more proton, the outer electrons on the shells are being pulled in by the nucleus, making the atom smaller. So let's observe lithium. 3 electrons, 2 on the inner shell, 1 on the outer shell. Beryllium, 4 electrons, 2 on the inner shell, 2 on the outer shell. And so this extra electron and the extra proton will increase the force of attraction, pulling the outer shell closer to the nucleus, causing the atomic radius to be smaller. Let's look at one more. Here's boron, and boron would have 5 for the atomic number. 2 on the inner shell and 3 on the valence shell. Again, one more proton is being added and one more electron as you go across, causing the force of attraction to be increased, pulling the outer shell closer to the nucleus, causing the atomic radius to be smaller. Now for the ionic radius, there is a slight change based on if you are a cation or an anion. Now for the cation, you'll have a decrease in size because of course you lose the valence shell to become smaller. Whereas for the anion, you would increase in size because of course you would form a new shell as you go across. And remember that we change from metal or from metallic properties to non-metallic properties as you go across the period from left to right. So now we look at electronegativity and metallic characteristics. Let's look at metallic characteristics first. Remember we said that we decrease in terms of from metals to non-metals. So going across the period, sodium, magnesium, aluminum, these are metals, and as you go across to silicon, phosphorus, sulfur, chlorine, those are non-metals. Now the electrons are less easily removed or lost from the outer shell from left to right. That is, from left, for example, in sodium, magnesium, and aluminum, you'd have 1 electron, 2 electrons, 3 electrons. Then it will be easy for these elements to lose the 1 electron, the 2 electrons, and the 3 electrons. Then, let's say a phosphorus that is in group 5. Phosphorus, it is very difficult for phosphorus to lose 5 electrons. So instead, it would gain 3. Sulfur would gain 2. Chlorine would gain 1, and of course argon is already stable, so it will not lose or gain electrons. So you now understand that the electrons are less easily removed from left to right, because of course every time you keep adding an electron and a proton, you increase what is called the nuclear charge. Very important term, because nuclear charge determines the force of attraction between the nucleus and the valence electrons. Electronegativity is a very important term that you will be seeing and using throughout your chemistry life. So let us try to understand this very important term. Now, first of all, the trend is electronegativity increases to the right. Now, you might be saying, what is electronegativity? Electronegativity is the ability of an atom to attract a bonding pair to itself. Now, what do we mean by that? This is very important. It is attracting electrons, but the electrons are normally in a bonding pair. If you can attract electrons more than another atom, then you are more electronegative. And it is always important to understand that in order to determine polarity. We looked at the polarity of water before. We looked at the polarity of hydrogen chloride or hydrogen bromide, because the Br and the Cl, they are more electronegative than the H. And in water, the oxygen is more electronegative than the H. Hence, water is polar. Let's look at electronegativity in a little more depth. Look at these two atoms in this molecule, A and B. Now, can you say which one is more electronegative than the other? Well, you can't just by looking at the two unknown atoms. At the moment, both atoms have the same electronegativity. So none is pulling the electrons closer to itself than the other. But suppose I increase the electronegativity on one atom over the other. Let's increase the electronegativity on atom A. Now observe what is happening to the atoms and the electrons that are present in the bonding pair here. You will notice that the electrons are being pulled closer to atom A and farther away from atom B. If the electrons are closer to atom A, then it means that atom A will gain a partial charge. Atom B would have less electrons because they are farther away from it, so they will have a partial positive charge. So when the electrons are close to one atom, you get a partial negative charge here. And when it's far away from the other atom, you get a partial positive charge. Now, this particular molecule is dipole or polar because we have one side being negative and another side being positive. Let's look at some real molecules now in case of hydrogen fluoride. Now, hydrogen fluoride is a gas, and we have one H atom being bonded to one F atom. Now, the fluorine atom is more electronegative than the hydrogen atom. Hence, it will pull the electrons in the bonding pair closer to it and farther away from the H. And so you should observe that the dipole should be in this direction, going towards the F and away from the H. And in terms of your charges, the fluorine should have a partial negative charge and the hydrogen should have a partial positive charge. And so you can see that the electronegativity of F is partially negative here, and the electronegativity of H is partially positive. So, in simpler terms, if I have H, and these two atoms are the same, then they both have the same electronegativity. Now, one electron is coming from this H, and the other electron is coming from this H. So they should be dead in the middle in terms of the bonding pair. So we call these two electrons here bonding pair. And they should not be closer to one H atom than the other. In the case of HF, where you have the bond like that, the electrons should be closer to the fluorine atom because the F or the fluorine atom is more electronegative than the hydrogen atom. Hence, it pulls electrons closer to it and farther away from the H, giving the F a partially negative charge, giving the H a partially positive charge, and you observe that we now have a dipole molecule. Hence, HF is a polar molecule. So in terms of electronegativity, normally the nonmetals are the atoms that pull electrons towards themselves. And remember that nonmetals are the ones that are involved in covalent bonding. So electronegativity increases across the period, going to the right and away from the left. Let's move on to the oxides of period 3 elements and examine their melting points. Now, the oxides formation, we're going from sodium, magnesium, aluminum, and so on, and these are metals. Now, the two metals, sodium and magnesium, they form basic oxide. So remember that sodium is in group 1, so it's Na+. Magnesium is in group 2, so it's Mg2+. So we can form or write the oxide for sodium. That would be Na2O. And this is a basic oxide. For magnesium, it would be MgO. And that is also a basic oxide. Now, the aluminum is considered to be an amphoteric oxide. So we write Al2O3. And this is your amphoteric oxide. Why is it considered amphoteric? Well, it has both acidic and basic properties. If it has acidic and basic properties, it means that it will either react with an acid or a base. So that is considered to be amphoteric. The other oxides, like silica, SiO2, that is silica or sand, this one is becoming more acidic now as we move into the nonmetals. Phosphorus can form two oxides. It can form phosphorus 3 oxide, which is P4O6. And we can form phosphorus 5 oxide or phosphorus pentaoxide, and that is P4O10. So those are your two oxides of phosphorus, and these are acidic. Sulfur can form the oxide SO2 as well as the oxide SO3. And you will see the importance of these oxides in forming sulfuric acid. And finally, the oxide of chlorine. You could simply call it chlorine oxide, or you could call it dichlorine heptoxide. And that is Cl2O7. So the dichlorine will come from 2 chlorine atoms, and the hept come from 7 oxygen. And these are your oxides going across the period 3. Remember that trends in period 3 will be similar to trends in period 2. So if you get questions based on period 2, it should not be that difficult to understand, even though we're studying period 3. Let's move on to melting points. Now, sodium to aluminum, and these are metals, you will increase steadily in the melting point. Why? Remember that as you go across a period, the number of electrons and protons increase. And so we'll have more mobile electrons in aluminum than magnesium, and magnesium would have more than sodium. And so the greater the amount of mobile electrons to the cations in the metal, the greater the melting point will be, because the forces of attraction will be stronger. Silica will have a very large melting point because the structure that is formed is a giant molecule. Now we call it a macromolecule because it is a very large molecule formed from the covalent bonding between the atoms of Si and oxygen. As you go across, you will notice that the melting point will decrease because we're moving from metallic bonding to covalent bonding in terms of giant macromolecules to simple molecules. And so P, which is phosphorus, would decrease, forming P4 molecule. Sulfur would decrease, forming S8 molecule. And chlorine to argon will also decrease because chlorine, of course, formed the simple molecule Cl2. So going across period 3, there should be a general decrease in melting point. Because of what? The type of bonding that takes place determines the type of molecule that was formed or substance that is formed. In terms of the metals, metallic bonding is responsible for the large melting points. In terms of silica, the large increase in melting point, which means that it is much stronger than the metals. So you should observe, if we have a graph like this to show you in terms of melting point here, then you'll see increasing from sodium to magnesium to aluminum would be steady increase based on the number of mobile electrons that are present. But you should observe a very large or sharp increase going from aluminum to silicon, because silicon would form that large macromolecule in terms of silica, which is SiO2. Strong covalent bonds, large melting points. And then when you form simple molecules, the melting point will decrease drastically. And it will continue to decrease because the molecules are becoming smaller. So this gives you a good idea of the trend in melting point going across period 3. Now here are some general trends about the periodic table that will assist you in understanding the trends in period 3. And we remember that some of the things was discussed earlier in terms of atomic radius going this way. Of course, it will increase. Ionization energy. We discuss metallic and non-metallic character. And of course, electron affinity, which was not discussed, but it's simply the ability to attract electrons. Now, these electrons are not in a bonding pair, which is where the difference is with electronegativity. So remember that electron affinity is different from electronegativity. Electronegativity is just the ability to attract electrons in a bonding pair, while electron affinity is the ability of an atom to attract an electron, with no mention of a bonding pair. This concludes our lesson in trends looking at period 3 elements, and in our next topic we will move on to bonding, mainly ionic and covalent bonding. See you then.